Hello, I'm Busa Aktash from the Harvard Biorobotics Lab, and for RoboSoft 2020, I'll be talking about how we can achieve tunable anisotropic stiffness using square fiber jamming. So rigid robots are fast, precise, and they're strong, and soft robots are conformable, adaptable, and they're safe. And we can achieve the best of both worlds using variable stiffness. There's many different ways to achieve that, but in this case, we're going to be focusing on jamming. What is jamming? So we're focusing on fiber jamming, so we'll take a pile of fibers, put it in an airtight envelope, and finally attach it to a vacuum. And let's see what happens. So on the left-hand side, you're seeing it with the vacuum on, and on the right-hand side, you're seeing it with the vacuum off. When you turn the vacuum on, you create a pressure differential between the inside of the bag and the outside of the bag, squeezing these fibers together, increasing the kinematic and frictional coupling between the fibers, and therefore changing the mechanical properties, particularly the stiffness. So now we have a tunable bending stiffness element. There's different ways to achieve that through jamming. There's also layer jamming, which has been studied much more often. Why are we looking at fiber jamming particularly? Because it has unique advantages. Namely, it has tunable bending stiffness in multiple directions, which is much more useful for applications such as endoscopes and manipulators when you do have forces coming from multiple directions. Whereas for layer jamming, unfortunately, we have tunable bending stiffness in one particular direction. Why am I saying unfortunately? It's because layer jamming has some great advantages that fiber jamming right now does not have. One is it's reliable and repeatable behavior. So right now, these are two animations to kind of show that behavior. So on the left-hand side, you're seeing the layers just slide with respect to each other. That's the only motion. But on the right-hand side, when you're bending the fibers, they kind of roll around each other and rearrange themselves. And that will change the overall cross-sectional area and therefore the overall bending stiffness of these structures. So fiber jamming with circular cross-sections really do not provide repeatable and reliable behavior. And related to that is the modelability. Because I know where the layers are with respect to each other at all times, they're not randomly rearranging, I can come up with pretty straightforward theoretical models of the stiffness behavior of layer jamming structures. Whereas this is not as easy as for fibers because the contacts between the fibers are kind of lines that are constantly twisting and turning and moving, so it makes it much harder to model. To address this problem, this trade-off, we're proposing square fibers. So the same thing as fiber jamming. But instead of circular cross-section, we're taking fibers with square cross-section, putting it in an airtight envelope, and attaching it to a vacuum. What are the unique advantages? So the square fibers create kinematic constraints, the geometry of the square fibers. You can kind of see here that they're no longer rolling around with respect to each other, and the contact surfaces between them is pretty constant. So this allows us to have much more repeatable and reliable behavior. Related to that, we have much more modelable behavior. So if you can see on the left-hand side, it's as if you're bending 3 layers, and on the right-hand side, it looks like you're bending only 5 layers. Because we know where each square fiber is with respect to the other one pretty easily, and it does not change throughout the deformation, we can easily model the behavior of this structure. And that's why in this study, we're going to provide a full closed-form theoretical model of the force deflection behavior of these structures in different directions. We're going to experimentally validate this model, and finally, we apply it to a manipulation use case, in this case, particularly an endoscope. So let's start with the model. What do I want from the model? So in the middle, you're seeing a head-on view of a square fiber jamming structure and many, many red arrows. So no matter which direction that red arrow is pointing, I want to know what my force deflection behavior is going to be. And in particular, I want to know the force I need to apply per a given deflection. That's the stiffness behavior, and according to Euler-Bernoulli beam theory, that scales with material properties and geometric properties. And in this case, the material property is Young's modulus, and the geometric properties are the moment of inertia and the length. In the study, we're particularly going to look into moment of inertia because we're interested in how the number of square fibers and the dimension of these fibers affect my stiffness behavior. So let's start with the unjammed stiffness. So when the structure is unjammed, we're assuming that all the fibers are completely independent of each other. So in this case, we're looking at a 3x5 array. It looks like we have 15 different fibers just bending together. So the moment of inertia in this case is just going to be 15 times whatever the moment of inertia is for a single fiber. And that leads to an overall low stiffness compared to when we jam it. Because when we jam it, we look at it as one continuous rectangular beam. And now we're bending it about the axes where I have 5 fibers. So the dimensions with the 5, with the N1 is going to dominate in this case. So it'll be 5 squared times the original. So it'll be 25 times stiffer than the unjammed state when I'm pushing it in this particular direction. Now let's push in the complete orthogonal direction, shown by the yellow arrow here. Now I'm bending it about the axes where I had 3 fibers. So in this case, the 3 will be dominating the moment of inertia equations. It'll be 3 squared times the original, so it'll be 9 times stiffer than what I had compared to the unjammed stiffness. So far I only showed sort of the two orthogonal directions because they're easier to show, but we can have a full model with all the different angles and how that changes throughout the regime. And you can see the maximum stiffness happens when you're along the bending about the longest axes, and the minimum stiffness happens when you're bending about the shortest axes. So this plot is only for a given structure, sort of a given N1 and N2 value. But what if I want to understand the relationship I have between the stiffness and the geometry? This plot is to show that. So this is a stiffness ellipse plot. In the x direction, you're looking at the stiffness about the x-axis, and on the y direction, you're looking at the stiffness about the y-axis. You can see here that in the very middle, we have this gray circle. That's a 4x4 matrix of square fibers. So it's not surprising that it's a circle because it'll behave isotropically. Square beams behave isotropically. But once I start adding fibers and turn it into a 5x4, a 6x4, a 7x4 matrix, my stiffness ellipse starts looking more like an ellipse, and finally it starts having dimples and looks like peanuts. So you can see as I change the ratio between the two dimensions of my square fiber jamming structure, I can change the anisotropy. So I can program into my structure what I want the ratio of the stiffness between the axes I want to be. Another thing to point out is the tiny circles in the middle that we zoom into on the right. Those are the unjammed versions of the structure. Again, no matter how much of a rectangle we have, our unjammed stiffness will still be a circle because they're independent fibers of each other. So now we looked at the stiffness, the jammed stiffness versus the unjammed stiffness. But is that the full picture? Will that give me the full force deflection behavior? No, there's actually a little bit more. So if I keep pushing on these structures, at one point, these dotted lines I've shown here in red will start slipping. So the tip of the structure will kind of look like this. It'll start slipping about these four separate surfaces. And this will happen when the shear force in the beam is able to exceed the frictional force in between the fibers. And after that, what's going to happen is we're going to treat it as if there are 5 separate rectangles, because now they're freely sliding with respect to each other. So I have a much less stiffer slope after that particular point. Let's try pushing it in the other direction now. Now along the axes where I have 3 fibers, I had an overall low stiffness initially to begin with, and then it'll eventually slip along those 2 surfaces, and then it'll sort of behave like 3 rectangles, and again have an overall lower stiffness after the slip point. And here what I'm interested in is what the slip threshold is, so I need to find the point at where I'm able to exceed the frictional force, and then I also need to know what my post-slip stiffness is, so that I have the full force deflection behavior. So let's start by looking at the slip threshold. So now we're looking at a fiber jamming structure head-on in the XY force space, and I'm pushing it only in the X direction where I have only 5 fibers. And the blue line shows the force threshold, and before it, it's continuous, and after I cross that threshold, it's going to start slipping along those blue planes. This line that I drew is governed by this particular equation, and it's 2/3 mu PA. Mu is the coefficient of friction, and P is the vacuum pressure. So mu times P is the shear stress in the beam that I should not exceed at all if I do not want my fibers to slip. And the A is the cross-sectional area, and we need that because the shear stress is distributed along the entire cross-section. And the other thing is the 2/3. That comes from the fact that shear stress is not distributed equally throughout the beam. It'll be much higher in the middle of the beam compared to the edges where it's 0. So now let's push in the complete other direction and about the axes where I only have 3 fibers. Now I've shown it with a pink line. Before the pink line, everything will be cohesive. After the pink line, the pink surfaces will start slipping. And this line will be governed by the same exact equation, actually, because the coefficient of friction and the pressure does not change with the direction, and the cross-sectional area does not change. So then we can kind of see that it's a square, and it's not direction variant, the slip thresholds, which is an interesting thing to point out, even if our structure was very rectangular. So far we've only pushed in the only X and on the only Y direction. So let's see what happens when we push in a direction where we're off axes. In particular, we're looking at now kind of a 60 degrees from the x-axis. So first everything is cohesive, right? Then we cross the pink line, the pink surfaces start to slip. And finally, we cross the blue line and the blue surfaces start to slip. So we have 2 distinct points of slip compared to layer jamming where you only have 1 point of slip. So that's one unique thing about square fiber jamming structures. So using this sort of 2D force space now that I know all of the force thresholds, all the slip thresholds, I want to make sure that this entire force area has defined stiffness values. So let's start with middle. So that's the jam stiffness, right? That's before the structure is slipped at all. And we had defined that with this equation that corresponded to the peanuts, the stiffness ellipses. The corners are going to be when both axes are slipped, so that's going to correspond to the unjammed stiffness because now they're all free from each other. And now we hadn't yet defined the other corners, but those are pretty easy to define too because they're just rectangular shapes that are completely separate. So for the blue edge, in this case, we'll treat it as 5 separate rectangles. And for the pink case, we'll treat it as 3 separate rectangles after those pink surfaces have started to slip. So now if I, again, load it in the particular direction, 60 degrees from X, we know the unjammed stiffness. We know the stiffness after it has slipped in the pink plane. And then we know the stiffness after it has slipped in both planes. So here's a sweep of sort of 15-degree increments and showing how the force deflection behavior changes. And so I have a full theoretical model that can show me the force deflection behavior of any square fiber jamming structure. And a few interesting things to point out. If you're pushing only in the X direction, Y will never slip. If you're pushing only in the Y direction, your X direction will never slip. And if you're pushing 45 degrees between X and Y, they will slip simultaneously at the same time. So now we need to experimentally validate this, obviously. So to remind you, on the left-hand side, we have the full force deflection behavior for different sort of degree increments. And on the right-hand side, we have the ellipsis that we want to validate. And these are results from our experimental validation. We did 3-point bending with fiber jamming structures in a 4x10 array in this particular case. And first of all, let's look at the unjammed. You can kind of see that they're all almost have the same exact slope. And we know that it's isotropic, so that's what we had expected. And for the jammed state, you can see that the lowest stiffness happens at the yellow, so when we're bending about the shortest axes, and the highest stiffness happens at the highest one. And the right-hand side plot is extracted from the left-hand side plot, and we can kind of see the little dimple as well and the peanut-shaped stiffness behavior. So we know that we have a tunable anisotropic stiffness in our jam state. So now we want to apply this. So in this case, what we're doing is we're taking a split tube. Those are the tubes that you have with a slit in it that you kind of wrap around cables to make it look tidy. And we're passing through our square fiber jamming structure. This is a 3x5 structure made out of rubber. And in the unjammed state, you see that it comfortably sort of passes through it and it conforms to the entire shape. In the jammed state, though, because it is much, much stiffer, what's happening is it has a higher tip force and now it's kind of sliding outside of the slit. So it's able to exceed the force that's required to kind of keep inside the tube. So now this is kind of an application to show, and one particular application that could be useful is an endoscope. And when you're using an endoscope, you want to be soft during insertion. When you're going through these windy paths of the body, you want to conform to it without exceeding certain forces, without putting too much force on the tissues that you're going through. And then finally, when you're where you need to be, you want to be stiff in a particular direction when you want to execute your task. So let's start with the insertion component. So now you can see that we had this in this experiment. What we did was we had a tubing that had bending in 2 different directions, and then we put in a square fiber jamming structure and feed it in with a sensor. And we measured our feeding force. And you can see the 2 bends are where the increases in force happens. And obviously the unjammed case, the gray line, is much lower than the jammed case, which is as we expected. We have a much lower feeding force, so it means it's much easier to go through these windy paths when I'm unjammed. And it doesn't matter which bending direction I'm in as well. So you can see in both bending directions, I'm able to reduce my feeding force by a lot. So now I've completed my path. I'm where I need to be. Now I want to make sure that I can tune my stiffness in the way I want to. The way we experimentally tested this was to pull on this structure from different directions with an equal weight and see how much it deflected. So in this plot, you're seeing a deflection plot given a constant force. The gray dotted line is showing the unjammed state. So it's a bigger circle, which means it's deflecting more, giving a constant force, so it's less stiffer. So these are compliance ellipses rather than stiffness ellipses. And when I jam it, I see that it's a much narrower ellipse. It's much stiffer on the longer axes where I only had 5 fibers. And it is anisotropic as I expect it to be. So now I have this endoscope, can be unjammed when I'm going to my path, and once I'm here, I can be stiff in a particular direction given the kind of task I want to complete. So overall in this study, we propose a new structure that has tunable direction variant stiffness. We provide a theoretical model of the mechanical behavior of these structures. We experimentally validate the model, and finally we applied it to an endoscope use case scenario. Thank you so much. My email is right here if you'd like to contact me with any questions.